Imagine this. You're a research scientist with the Keeling and Weiss labs at Scripps Institution of Oceanography, collecting air samples so that you can analyze the movement of greenhouse gases. To get accurate data, you want to collect samples of air high off the ground so that they're well mixed and representative of the surrounding region, rather than being skewed by localized emissions. Your traditional options are to use a weather balloon or sampling tower, but those can be expensive and impractical for sampling a wide range of locations.
This is where drones come in. If you can take samples using drones as a platform, your system becomes much more versatile. To pursue this solution, our project's objective is to design and test a mount that attaches a 3D wind direction and speed sensor, an anemometer, to a drone. This, in combination with temperature and pressure sensors, can tell us whether the air around the drone is an ideal sampling location. Paired with our electronic system that logs data and streams it live to a ground computer, scientists can assess local meteorological conditions in real time for sampling and study. To succeed in this project, we had to fulfill the following requirements. First and foremost, the anemometer must be held high enough to avoid propeller interference in its measurements. Additionally, the mount must be easy to fabricate so that scientists with little machining experience can replicate the process. The mount also has to be made with tools available in the Scripps Sandbox Makerspace, the most convenient place for our sponsor to use. Regarding usability, the system has to be easy to deploy in the field, optimized for quick assembly and data logging setup. Finally, all materials must be weather resistant, especially against UV rays, to withstand outdoor field testing conditions.
Our design solution is composed of three main components: the mount, electronics and sensors, and the data acquisition software. For the mount design, we needed to place the anemometer 1.5 times the propeller diameter away from the propeller plane to avoid data interference from the drone. We did this with 4 carbon fiber tubes attached to the drone arms with 3D printed ASA clamps, an ASA platform that connects the 4 legs to the top, and a carbon fiber mast that extends from the platform and ends in an ASA adapter to mount the anemometer to the mast. Now that you know about all the parts, you're ready to conduct your experiments. Luckily for you, it's easy to assemble. All you need is a Phillips-head screwdriver, 2 Allen keys, and a wrench. To assemble the mount, snap the 4 mount legs onto the drone arms. Then take the platform with the electronics box screwed on to connect all 4 legs. Then thread the anemometer wire through the mast, connect it to the cable coming out of the electronics box, and then put the mast on the platform. All that's left is to tighten down the screws on the clamps, platform, and anemometer mount.
The Raspberry Pi is the main processor for all of the sensors in the design. Data from the anemometer first goes to the USB adapter, which translates it from RS-232 protocol to USB protocol. This component also converts the 5 volts of power from the Raspberry Pi to 12 volts in order to power the anemometer. The data is then collected and logged on the Raspberry Pi via a USB-C to USB wire. The design also includes a suite of sensors from the 2021 to 2022 Spring MAE 156B Team 15 that record temperature, pressure, altitude, and humidity. These sensors communicate with the Raspberry Pi via a I2C inter-integrated circuit protocol HAT on the Pi.
For the software, we wrote a Python program that is executable on the Raspberry Pi that parses the data from the sensors, logs the data to a local CSV file on the Pi, and displays the data on the Raspberry Pi's terminal, which is displayed on the ground computer's terminal via SSH, or Secure Shell Protocol, and also graphs the live data on a web dashboard, viewable by typing in the Wi-Fi's IP address on any web browser from any device. However, one challenge we faced was how to make the live data transmission and Raspberry Pi control more reliable. If there was no stable Wi-Fi connection for the ground computer and Raspberry Pi to connect to, due to reasons such as many interfering signals, for example from nearby phones, cars, laptops, or other Wi-Fi signals, or if there was no Wi-Fi to connect to, we cannot see the data live and could not connect via SSH to the Raspberry Pi to start the data logging code.
So we did more research and found another way to transmit small data bytes via LoRa communication, aka long-range communication, which uses radio waves of up to 915 MHz to transmit packets of data over long distances. Most LoRa boards are rated for up to 5 kilometers, however it varies due to obstacles and other interferences in the area. We also programmed the Raspberry Pi to start the Python program upon startup, which occurs when you plug it into power. So we do not need to SSH in order to start the data logging process. Once we go to an area with Wi-Fi or better signal, we can use the Raspberry Pi's onboard hotspot to SSH into it and turn it off with one command line. After all of this troubleshooting, we were able to get LoRa to transmit a counting data to display on the ground computer at a distance of up to 1,167 feet while stationary and through one building. And while sending sensor data, we were able to communicate up to 745 feet away while flying and through multiple houses.
During development, we conducted 4 flight tests off of Scripps Pier in coordination with weather balloon launches by the Center for Western Weather and Water Extremes. These tests allowed us to compare our measurements to conventional balloon data. Examining the initial flights showed clear correlations between our drone's gathered data and the weather balloon measurements. After further testing by our sponsor, the drone will be ready to independently investigate regions previously inaccessible to scientists.
Thank you for watching. We hope you can use this to inspire your own research projects. All our resources are open source thanks to grant funding from the Scripps Institute of Oceanography at UCSD. Please see our website for more details.